Sorry, my notes got out of order. Cool. Any questions? I talked to some of you just now, but anything? Any thoughts or questions before we get into some new stuff? So we're just going to keep building on the same. So where we're about to go is we're about to do the same kind of calculation again, just in a slightly more complicated setting with now 2 particles with 2 different scales to see how that works. So I've really been trying to emphasize this, we're focusing on these continuum techniques using DimReg because it's just practically the way the majority of calculations are done, and it has many appealing features, especially at one loop. Essentially, you can read all of the answers for the loop diagrams out of books, so you just have to be careful about symmetry factors and color factors maybe, but the loop diagrams themselves are usually pretty straightforward to calculate, even in more complicated settings. But what is not made manifest by DimReg and this continuum approach is heavy particle decoupling. Okay, and the reason for that is because the renormalization scheme is mass independent, right? We're actually renormalizing using dimensional regularization, right? We're changing the dimension of space-time in order to make our integrals convergent, and then we're analytically continuing back to 4 dimensions, right? And isolating the 1/epsilon poles at one loop. If you were doing these calculations, say using a cutoff regulator, which I don't have time to do in detail, but there are plenty of resources in the literature that do these do a calculation much like this, where they first do it in a scheme with a cutoff, and then they show you how to do this in DimReg and compare the two for the beta function, for example. So if you do the calculation in a scheme with the cutoff, what you'll find is you'll get heavy particle decoupling happening even in the RGEs. So your RGEs have mass dimension built into them, and so you can actually explicitly see as you run the RGEs that when you cross a heavy threshold, for example, your beta function changes, right, as you take it across the heavy mass threshold. But that just does not happen for us in this continuum picture, right? The RGEs we derived yesterday didn't know anything about mass, and we're going to use them again today where we explicitly have a heavy mass parameter. And again, you'll see it even more sharply here that we have to sort of by hand impose decoupling, okay? And the way that we do that is by realizing this interplay of this continuum picture with effective field theory, okay? So that's the next thing I want to show you now. And unsurprisingly, just to be really concrete, we're going to pick our process. Phi goes to phi, okay? And we're going to work at threshold. Right, that's just going to simplify everything. We're not going to have to keep any explicit momentum dependence around. And my full theory, Lagrangian, is going to include, I'll call the coupling kappa between little phi and big phi, and the coupling between, or the self-coupling of little phi, and the full theory I'll call eta, the same parameter I used yesterday, okay? Actually, yesterday I guess we always called this C4 because we were working in the effective theory, but when I talk about the quartic and the full theory, I'll call this thing eta, okay? And I'm not going to write them, but there's 2 mass terms. This thing has a mass little m, this thing has a mass big M, and we want to work in the limit where little m squared is much, much less than big M squared, okay? So now for the first time, well, sort of at tree level we had this, but now at loop level for the first time we're talking about something where we have an explicit large separation of scales, okay? So we're going to encounter large logarithms, and we're going to need to resum them, okay? Yeah?
Yesterday we used the equation of motion at tree level to integrate out the x that is the higher degree of freedom. What about if we had calculated
So I mentioned this. So when you use the equations of motion, what you're really doing is you're doing a functional approach to effective field theory, and there is formalism for doing that at one loop. You basically take a log determinant. It's kind of, you compute the 1 pi effective action. There's a whole story there. That would be an entire lecture. So here I'm going to do this using diagrams perturbatively, and yeah. But there's a formalism at least at one loop for doing that in a concrete way. And I could point you to references, but yeah, I'm just not going to talk about it. Okay. Notice, by the way, but I'm glad you asked that question, because notice that I changed the theory from the one we did at tree level, right? The one we had at tree level, I only had one factor of capital phi, so that I could integrate out capital phi at tree level just right through the diagram exchanging capital phi. Now, because I don't have that diagram, right? This is non-generic, but although you could eliminate that by enforcing a Z2 symmetry in the full theory, whatever. But here, right, I don't have that type of interaction. Instead, I have just this little phi squared, big phi squared. And so that tells me that if I want to integrate out big phi squared, right, it's only going to come in affecting the little phi physics at one loop, right? So in particular, right, at NLO, we have two sets of diagrams. We have the loop of little phi exchange that we were studying yesterday afternoon, and then we have a loop with big phi exchange, right? So these are my little phi's, and I'm going to use solid lines for big phi, right? And there's channels to worry about, right? So I'm not going to. I'll write the correct factors. I'm not going to actually derive every little detail, but just realize there should be 3 times sort of all of this for the channels, right? This plus this. Okay. Good. So, oops, I'm using A's, not M's. So the full theory amplitude is simply, and of course, right, that's NLO, but I should add the tree level, right? So I have tree level exchange, so I get an eta. Notice, again, in my conventions, right, the Feynman diagrams calculate IA. The Feynman rule would have an I here, but I dropped them, okay? So we have eta, and then we have 3 over 32 pi squared times eta squared log mu squared over m squared, plus that 2/3 that came from the S channel. And then we also, now we have a new thing, which is 3 kappa over 32 pi squared times log mu squared over big M squared. And then there's stuff that I'm not writing. Okay? Squared, thank you. And this ... here is because, partly because there were little m's in principle that came from the S-channel diagram, right? Because with the S-channel diagram, you actually had to propagate that momentum through here. And so if you do this in detail, right, if you keep all the factors of little m and big M, then you just get a messier log, right? But I really want to focus on this limit where big M is much, much bigger than little m. Okay, so that's a part of what's captured in the ... here. Okay. Good. So we see in the full theory we have a problem, right? We have a large separation of scales. Our full theory has problems with perturbation theory. If eta and kappa are perturbative, there's still no choice of mu I could make, right? As long as if the separation of scales is very, very, very big, right? So these logs are large. If I choose mu of order little m, then I get a large log. If I choose mu of order big M, then I get a large log, okay? So I got to do something, all right? The example I showed you yesterday afternoon, in principle, right, you could have just always evaluated the renormalization scale of order the threshold, right? And you really, so I was kind of artificially causing a problem yesterday to just go through the exercise of running the RGEs, but now you're forced to deal with this, okay? You can't get around it, right? Good. So any mu gives a large log. And the RGEs don't solve the problem. So let me just write them So we have d eta, d log mu squared. By the way, just to make this point again, I probably won't mention this again, but I'm not writing the r's. Everything's renormalized here, and I'm not putting the tildes on the mu's. We're in the MS bar scheme, okay? So we have 3 over 32 pi squared, eta squared minus kappa squared, and we have d kappa squared, d log squared, mu squared, sorry, is 1 over 8 pi squared kappa squared plus 1 over 32 pi squared kappa eta, okay? So I didn't derive these for you, but you would use exactly the same techniques we used yesterday, so I'm not going to go through all those details. Here, right, this is just coming from these diagrams, right? So you have the eta squared diagram and the kappa squared diagram. Here, you have the analog of this diagram where you just flip big phi and little phi, but you also have a kappa eta diagram, right? Because you can write a diagram like this. And that renormalizes kappa, right? Kappa is the cross-quartic. Okay? I'm being non-generic here. I'm being a little bit sloppy. Actually, yeah, so does anybody, what's the sloppiness here? Does anybody see it? I'm not including an effect that I really do need to include if I want to do this consistently. Sorry? Which one? Yeah, well, I'm not worried about the mass renormalization, actually. So that's not going to infect any of the stuff that's happening here.
If you want to renormalize the kappa, you need another tree-level diagram, right?
I don't think
You
so.
need this one without the loop, right?
This one.
This one without the loop.
Oh, but I have it. It's here, right?
No, it's a diagram, right? Like you added the 4-point function tree level, right, to this one. So on the left.
Yep.
So you need the equivalent one for kappa if you want to renormalize kappa.
So I've already done that when I wrote this RGE. I just skipped those steps. Okay?
Yeah.
There's something else that I'm missing.
The one with capital phi.
Exactly. Very good, right? So this kappa, right, can generate a diagram for me with 4 capital phis, right, at one loop. So I actually, this is actually cheating, but again, I'm being non-generic because I'm doing this all on the board. If I ran the RGEs sort of beyond summing one loop, I would just start to be generating the quartic for big phi, okay? And in fact, this question came up after the lecture yesterday. If I wanted to actually renormalize this theory, even if I wanted to set it to 0 at some high scale, I actually need to include that coupling so that I have the counter term so that I can eliminate all the divergences in this theory, okay? So again, I've warned you over and over that I'm going to be non-generic. This is just another non-genericity, but it's conceptually fine to look at this. I'll make the point without dealing with that, but there's something a little bit funny about taking a large separation of scales and not including that. Yeah.
Sorry, so maybe I'm misunderstanding what you do. I thought we were integrating out the large phi.
I haven't done that yet.
Oh.
All I'm doing is I'm asking, so I want to ask, I've picked my process, right? And I want to be able to calculate this process in a controlled way, okay? And so I started by just calculating it one loop. And what I told you is this is the answer, and clearly there's a problem. So we want to RG improve. In order to do that, we would just calculate the RGs in this theory, right? And we see, maybe I didn't make this point quite sharply enough yet, but the RGEs, these are just differential equations now. There's no big M. So they know nothing about decoupling, right? So I would run these RGEs from infinity down to 0, right? And I would think that my my eta renormalization would always get contributions from sorry, got this backwards. My eta renormalization would always get contributions from kappa, right? But we know that can't be true just from the intuition that heavy physics must decouple, okay? So that's the puzzle that we're going to solve with effective field theory. I just want to be, because we're talking about details here, I just want to be clear that I'm cheating a little bit because I haven't included the extra terms from the big phi to the fourth, okay? So I just want to make this small point.
But in your EFT, you're not going to include that. I mean, even if you were not cheating, right? I mean,
Correct, and that's exactly why I didn't include it. Yeah, but yeah.
I'm a little bit confused because now we have 4 diagrams or more to renormalize kappa, right? Because there is also 2-point tadpole diagrams, which are the one-loop mass diagrams for 3 capital and 3 small, which are also depending on kappa, right?
Oh yeah, of course, but I just renormalized the masses the standard way.
So there is also.
I'm working in renormalized perturbation theory, so I'm not doing every gory detail, right? I have renormalized masses, I have renormalized couplings here, right?
But kappa will not. Is kappa going to play a role on the mass of the small field?
Absolutely, yeah, and we're going to do that next.
Okay.
Yeah.
So just to make the point clear, I understand the simplification of not taking the large phi to the fourth term, but in principle, if you want to do this correctly, as you said, you can try to principle subscript to 0.
Yes.
But if you were to do it properly, you would need to take all of these 3 operators, let them mix with each other. And
Correct.
see what happens.
Exactly. Yeah. That's right. So I would have a third differential equation here, right, for the running of that coupling, whatever you want to call it, eta prime or something, right? Yeah, absolutely. I just don't need it to make my physics point, so I want to keep the expressions as simple as possible. Good. Very good. Yeah, so again, there's no mass scales in these RGEs, right? Again, I just want to emphasize if we had done this with a regulator that depended on a mass, like a cutoff regulator, our RGEs would have been taken a form that would have explicitly decoupled the mass, okay? So there's a puzzle here that is specifically due to our choice of regulation scheme, okay?
With the cutoff, you said what?
These, I would get different differential equations. They would actually include decoupling it. I'm not going to bother showing you that, but there's this Appelquist-Carazone paper. If you're interested in this kind of stuff, and you guys seem very interested, that's an awesome paper. Definitely would read it. It's super clear. But this was a real puzzle. I don't remember when that was written, in the 70s maybe, when people were, inventing dim-reg and trying to understand all of these effects, right? And so they proved for the beta function that heavy quarks decouple, right? Heavy physics. They did it for fermions. And so they actually, there's some really nice stuff in that paper which addresses exactly these kind of issues. They don't really talk about it in terms of EFT. What they do is they just enforce, they say, look, in the massive scheme, you get decoupling, right? You should get decoupling. So in the massless scheme, like dim-reg, you just enforce decoupling in the beta function by hand, okay? What I want to teach you is a little bit more of a systematic way of approaching it that justifies putting that theta function into the beta functions, okay? Which is something you maybe have done either in class or in research, okay? And in particular, something that's really nice about the effective theory approach, so I always hated that theta function thing because it didn't seem to be improvable, right? It's like, well, fine, you decouple it, so if your beta function, it's like in QCD, it's 6, or, and then you hit the top quark and it's 5, and you're just doing this with a sharp theta function, that's clearly not capturing the physics correctly. You would want to, order by order, improve this. It must be some smooth shape, right? And in fact, effective field theory is a really nice tool. It's not the only one, but it's a really nice systematic tool for, in principle, being able to calculate the shape of the decoupling effect on the beta function, okay? In exactly the way we're about to do. My marker's dying. So,
Can you add the to the reading list?
can I add, sorry?
I can't remember the first name.
Oh, Appelquist-Carazone, yeah. So I could generate a reading list for you guys. All of this stuff is cited in my so if you look in my lectures where I do this, I cite that paper really prominently and a bunch of others. Yeah. So it should be really easy to find. Every reference I'm going to refer to is in there. But so maybe I'll say that, and then if you're don't hesitate at all to message me about anything. So send me a quick email if you can't find something. Be happy to be of use. Okay, all right. So we're doing effective field theory, right? We want to solve this problem. So what do you think? What tool do we need to use? What's the key word here? We have a high scale theory. We have our EFT. What do we need to do to make them give us the same predictions? We match. So let's match. Oh my goodness. this one is also. I was okay. Okay, so we want to match onto an EFT at some scale. We're going to call it mu m. Okay? This m is playing two roles for us. It means matching, but of course, intuitively, right, we're going to decouple the heavy physics at the mass of the heavy particle, so it's also the scale of order the heavy mass. Okay? But critically, it's not exactly equal to the heavy mass. It's an arbitrary choice of scale, right? Just like a renormalization scale. And in particular, you can play around with this mu m, and you can kind of see that essentially gives you a sense of the uncertainty in your calculation of the decoupling effect, right? Which, of course, as you go to higher and higher order, that uncertainty will be softened in the way all of these kinds of things are in perturbation theory. Okay.
So this runs from the phase space of the theory, right? I mean, each different mu gives us a new theory, a different EFT.
Yeah, I mean, you can. Yeah, you can think about it that way because it changes the couplings. Yeah, but yeah. Good. So so here's the idea, just to really belabor the point. We have some mu high, right? Let's say, just like yesterday, that's sort of that's the theory where the scale where the theory is defined, some deep fundamental scale, right? Maybe the gut scale or something. We have this range of scales from the gut scale down to our, say, SUSY breaking, or our stop scale, right? If you think about this as some SUSY particle. So this is going from the gut scale where our SUSY particles get their mass down to the mass of those particles. So this is where the full theory applies, say the MSSM, okay? I'm betraying my age. So we have the full theory. We go down to the scale m, right? And now at this scale m, we want to decouple the heavy physics. We want to match onto an EFT. And we want to go down to the scale little m squared. And there will be some associated renormalization scale in the EFT, just like we had yesterday. Okay? So, are there any questions about this picture? Okay. And this, right, this is this, okay? Again, I really want to emphasize, right, mu m is arbitrary. It's of order big M to make the log small. I'm going to make that very, very concrete in just a moment, but it's not equal to big M, okay? So the scales are here, and the sort of characteristic energies that it's associated with them are here. This choice is made to make the logs all small, okay? So here, we were screwed. We had one renormalization scale. We could not simultaneously make all the logs small. And the magic of EFT at some level is that simply what it does is it separates scales for us. Okay? So it gives us a concrete tool to isolate the different scales of the problem. And through the magic of EFT, we're able to take a one-scale problem or a problem with one renormalization scale, seemingly complicate it by now introducing these two renormalization scales and this arbitrary matching scale. But what that does for us is that essentially all we're going to end up doing is we're going to systematically be changing these mu's to the appropriate mu here so that all those logs can be small. Okay? So that's the strategy. And then I'm just going to show you how the math works. All right. So here's our process. We're interested in the one loop effect. So what do you think we need to have in our EFT? What parameters does our EFT, or what operators does our EFT need in order to model this physics, do you think? First of all, what do you think the degrees of freedom are? Little phi, right? Again, not the same little phi, right? This is a different theory, but something like a little phi scalar with a mass of order little m squared, okay? Good. And then what are the symmetries going to be? Z2, what else?
Why not scale? Wait, there's no scale.
Oh, there's masses. I just didn't write them.
Oh, right.
Yeah. Lorentz, right? We haven't broken Lorentz, okay? So it's going to look very much like, I didn't write the kinetic terms and stuff, right? But we're going to use all of that stuff that we did on the first day, right? We get the same kinetic term in the EFT. We have power counting in terms of little lambda, right? The same power counting we introduced in the first lecture, okay? And then what operator do we need? Or what set of operators? We need phi to the 4, and do we need anything else, do you think? For this. Yeah, just what operators, right? So we definitely need phi to the 4, right? Because we're doing phi scattering, right? But, and the mass term, yeah.
And the normalization of the field itself.
And the renormalization, good. But probably not anything else, right? We'll see the next example we do. Yeah, boy, I'm going slow. We'll see the next example. We're going to need more operators, but here we'll only need phi to the 4. So our EFT is going to include, okay, now I'm just calling this a Wilson coefficient instead of a fundamental parameter, right? There's technically no difference. It's just conceptual. Okay, so this is our EFT interaction. And good. So now, so remember, when we matched in the full theory at tree level, what we did was we picked our process, and we said that process had to be equal at some scale. Although, since it was at tree level, really the scale dependence was kind of trivial, right? I even left it off. I made some comment about it. But now we're working at one loop. We want to do matching at one loop, so we have to be really careful about renormalization, okay? And here is a little dumb technical thing, but that's really tricky and something you might screw up if you were doing this for the first time, which is that, so we want to match, let's see, how do I want to write this? Actually have I'll leave the eyes off. So we have some so we take our full amplitude minus counter terms, and we subtract our EFT amplitude minus counter terms. So at tree level, this was trivial, right? This thing was 0. These were 0. We didn't have to include counter terms, and we just said, oh, let's set A full equal to AFT. And we'll solve for whatever the Wilson coefficient needs to be in terms of the fundamental parameters, right? But now we need to include renormalization, and what we're going to find is there's going to be a mismatch, okay? And we're going to call that the matching coefficient, okay? I'm about to do this super explicitly. But something I really just, this is this subtlety that we're not addressing here, which is the wave function renormalization. So one of the fun things about doing all this with scalars is that wave function renormalization doesn't come in until 2 loops, okay? That means I just don't have to deal with it, which is fine. If you're doing a real EFT calculation, you do need the wave function renormalization. And because you're matching a physical process at some scale, the wave function renormalization needs to be on shell, okay? So there's this it's just a frustrating little complication that you have to do this extra calculation to get the on-shell wave function renormalization because you're technically using LSD reduction when you do this, okay? So it's just a little aside comment, but if you actually go do a calculation or you read a calculation, you'll see all of a sudden that on-shell wave function renormalizations appear, and that's why, okay? It's because you really have to match the physical process, and so you need your external states to be on-shell, okay? Yeah. Either way.
Just when you say on shell, you mean I need to literally plot, let's say I want to scatter an electron from a proton, I need to plot the momentum of that actual electron, right? I mean, from the point of view that this is the actual momentum of the oncoming part.
Yeah. So in particular, right, there's all of this annoyance about scheme dependence and stuff, right? So you might think we're doing everything in MS bar. So I can compute wave function renormalization in MS bar, I can compute coupling renormalization in MS bar, et cetera, et cetera. But when for your external legs, because you're calculating something physical here, you actually have to use the on-shell wave function renormalization. So you just have to be careful about the scheme choice you make. So there's this, it looks really funny. It looks like you're mixing schemes, okay? But what we're going to do, and again, we're avoiding all of this here, but in practice what you have to do is you have to tack on-shell wave function factors for all your external legs to take into account LSZ at one loop. But then you can use MS bar for all the couplings, okay? So it looks very funny, but that's what you do to get the right answer. That also, for the 10th time, highlights that little phi in the full theory is different from little phi in the effective theory. When you calculate their on-shell wave function renormalizations, you'll see those factors are different, okay? So they really are different states.
Maybe I'm confused, but the one loop wave function normalization of the phi does not appear at one loop
Exactly. So here we're avoiding this, technicality.
of the phi. I mean, if I'm trying to match the operators in operator level, they still have the normal dimension. I mean, the normal dimension is equivalent to the wave function normalization. But I mean, phi to the 4 normal dimension.
So maybe let me do it because it's going to take into account all of the one loop corrections to the Wilson coefficients. That's what we're about to do. It's just, again, this is another thing I'm going to say a million times is we have to pick a process, right? And this is a step where that makes the fact that we picked a process very concrete, okay? When we calculate this matching coefficient, this difference between the two approaches, we're calculating that for some physical process, which means we need to use LSZ reduction, which means we need these on-shell wave function factors. That's the only point I want to make here. It's just because we're using scalars, we are not going to see that subtlety appear, okay? But yeah, if you, like I said, if you read a paper, for example, if you go look at papers I've worked on, like where we did resummation for Winos, which might be relevant to you folks since you're interested in BSM, you'll see these factors appear, okay? Yeah, anyway, it's just an opportunity for confusion, so I wanted to make sure I make the point. Good, so let me write now this in Feynman diagram language. So I'm going to give this thing just for, I'm going to call this mismatch between the full theory and the effective theory some vertex with a dot, okay? And that is equal to the full theory calculation minus the EFT calculation, okay? So this, we're calling the matching coefficient, is tree plus loop, one loop in the full theory, minus tree plus one loop in the effective theory, including counter terms, okay? So renormalized. Again, because it's physical, right? So I'm just calculating the physical scattering in both and looking at the difference. So tree is trivial. We have C4 at mu m equals eta evaluated at mu m. Okay? So this is exactly what we did yesterday, except now I'm being careful to include scale dependence because I'm going to renormalization group improve everything. Okay? And this is all being done at mu m, right? This is, okay? Now at one loop, we have C4 at mu m equals eta at mu m minus 3 over 32 pi squared kappa at mu m squared log mu m squared over big M squared. Okay, so I skipped some steps. I hope it's clear. Once I enforce this, these diagrams cancel, right? I'm, of course, also enforcing that my IR regulators are the same, okay? And in this simple case, that's really just saying the mass of little phi is the same in both theories, right? So that regulates the IR. If you didn't want to regulate the IR that way, you could do it any way you like, as long as you regulate the IR the same in both theories, okay? And it's going to be even sharper in our next example, but already we see that our EFT loops, right? This is going to give us a log of little m, right? just like we had explicitly on the board a minute ago. And one of the tests that you have the right EFT description and that you've regulated the infrared correctly is that you are analytic as you take all of your infrared regulators to 0. So in this case, the infrared regulator is little m. And as I take little m to 0, I better not have any logs of little m appearing at this high scale mu m, mu capital M, okay, mu match. And so that's, in this language, that's the statement that these diagrams need to cancel, because these diagrams generate logs of little m for me, right? So I better fix little m in the full theory equal to little m in the effective theory, okay? And that's what's happening here, right? So all of the dependence on the light loop goes away. That's because the EFT is specifically designed to generate those loops for us in the IR, okay? So that's what matching is capturing. Matching is saying, oh wait, in the full theory there's this extra crap that I can't capture in the EFT, but the magic of Wilsonian renormalization is that I can think of this as being shrunk to a point and becoming a local operator. So I can absorb this at the high scale into a local operator coefficient, a Wilson coefficient. That's exactly what we're doing, okay? We're just doing it in this technical way, right? And that's what this is. So this is a log generated through matching coming from this mismatch, right? The fact that this diagram is here in the full theory. And what we're going to do is we're going to absorb it as a boundary condition for our Wilson coefficient in the EFT, okay? Notice, right, as promised, I have mu m, and if I take it of order big M squared, or specifically if I take it equal to big M squared, this log dies. So I don't have any large log problem, okay?
For the IR, you said we're defining a matching and not having higher divergences?
Yeah, exactly. Well, so at these intermediate steps, if you set the mass of little phi equal to 0, right? So let me one step back. We're doing this at a high scale, right? So you would think that you should not be sensitive to the details of all the little masses of all the little particles, right? Because you're doing this at some scale deep in the UV. Up to IR divergences. So if I set all those little masses to 0, I would have an IR divergent theory, but the IR divergences, this diagram is not going to be IR divergent. It has big M regulating what would be the IR divergences, but these diagrams in principle could, right? And the only requirement is that the IR, the non-analyticity that's due to the IR divergences cancels in the matching, right? What's happening in the deep UV can't care about the details of the IR, so I should be able to regulate them any way I want. I just have to regulate them the same on both sides of the matching calculation, okay?
I'm just a little confused because usually if I had just the full theory or only the low energy theory, I would need to do inclusive cross sections to get rid of the IR.
No, yeah. We haven't gotten there yet though. So this is on the way to calculating the observable. But the whole point of EFT is that I capture the IR with the EFT itself. Okay, so all those things you're talking about, I'm going to calculate down here. And then I have to include inclusive blah, blah, blah. I either have a mass that regulates it or not. I have to do all those things like you say. Okay? But the UV can't care about those details. Right? That's sort of the mathematical manifestation of the decoupling. Okay? But just technically, what it does is it forces you to set these masses equal in this calculation. Right? Because that's the way we're regulating the IR. Okay? Okay. Good. So this, right? This is now C4 at mu m, right? That's where our EFT kicks in. So this is the boundary condition for our EFT RGEs. And our EFT RGE is simply dC4 d log mu squared equals 3 over 32 pi squared C4 squared, no heavy particle. Right? So there's no heavy particle in the EFT. So it's sort of trivial from, this statement, right? Once you're in the EFT, it's like, it's totally trivial. But getting to here in a systematic way that captures the one loop effects of the heavy particle is non-trivial. And if you want to get the decoupling right, order by order, you include it in the matching, okay? And in principle, this could include finite terms that depend on big M, right? And those are going to shift your definition of what you mean by C4 versus eta, right? So for example, let's say I picked mu m equals 2 big M, right? Then this term is non-zero. And in that particular choice of scheme, C4 is actually not equal to eta, right? So matching is giving me one loop corrections to the boundary condition for the EFT so that I'm getting decoupling correct, right? And I'm doing it systematically. So this, if you like, you can think of this as the correction to the theta function decoupling, right? This is just theta function decoupling. If I erase them, but the RGEs that you can almost see here, right? If I took those RGEs and I put a theta function in them and I said eta equals C4, I would get this, right? But the way to systematically improve that is to include the corrections in the matching, okay? Which changes the boundary condition. So it changes the relation between the fundamental physics parameters at the gut scale to my parameters at the low scale in the EFT, okay?
I'm sorry, I don't think I understood what you were explaining right now.
Okay.
I mean, I'm not sure, but this might become clearer as I see like the result, but why is A match not 0? Because in the tree level it was very simple. I want them both to be the same in high energy, and then I lower the energy, and then I know that they match at the high energy, and I'm looking at the low energy, so I don't care about what happens even above that. But now you're saying that A match is not 0, and I'm not sure if what you said right now relates to that, but this is still something I don't understand, so maybe it's the same misunderstanding.
Okay. So yeah, so let me try again. It's good. This is maybe the most important point. So so it's worth belaboring, right? The mismatch between the full theory and the effective theory is this diagram, okay? So at tree level, right, when I just did this, and I got this relation, right, it's sort of trivial. It's just saying we have a little phi particle in both theories. They have a quartic coupling. That quartic coupling should be equal to get the same predictions, okay? But now I have one loop contributions to that quartic coupling that are different in the full theory and the EFT. And so what matching is doing is it's capturing that difference, okay? So again, imagine that the etas are, handed to you by string theory, okay? So there's some calculation at the high scale. It gives you what the fundamental physics parameters are. And you want to make predictions at the low scale with no large logs. And so what I'm telling you is that the way to decouple order by order the heavy physics is through this procedure of using the EFT to separate scales. And when you hit a massive scale, you need to match onto an EFT description. And the mismatch between the quartic coupling in the full theory and the EFT is due to that one loop diagram. And we exactly include that through this change in the boundary condition for the RGEs, okay? And it depends, notice, right? It depends on the other parameter that was handed to you by the fundamental theory, kappa, okay? So there's a shift in eta, right? This relation gets changed by this perturbative amount, right? That depends on kappa. So that's capturing the impact of this diagram, right?
But the left-hand side, I mean, it looks like the right-hand side had this extra kappa, which is why it was encoded by the fact that you have C4 in your second row, but not in the first row. But it looks like the left-hand side is still 0, no? Because once I pass the second row to the left-hand side, I'm going to see C4 equals the eta plus the kappa from the other diagram, but I still don't see why isn't A match 0.
Okay, yeah, I see. Yeah. So, I mean, yeah, if you like, to match this picture, you can think of this as C4 match, which is okay. Sorry, I made that a little bit confusing. Yeah, C4 match, if you like, is the correction to this formula, so it would be without this eta. I skipped a step that sort of connected exactly to this picture. Okay, so what you do is you calculate order by order this thing, which is capturing the differences, right? So you have the tree level plus this thing, which is what I had written here. Sorry, now I see that was perfectly reasonable confusion. Yeah, okay.
Can you elaborate on the statement for the no heavy particle, because I don't think I understand.
Here?
Right.
Yeah, okay, so this, right, this is C4. This is the Wilson coefficient in the EFT, right? The EFT only has little phi in it. It doesn't know about big phi.
That's what you mean.
Yes.
Sure.
Yeah. So it's it's like completely trivial, right? Once I say this is my EFT, it only has this one state in it, right? I calculate the RGEs in the EFT, right? And I've decoupled the heavy particle. There's no dependence on any other loop, right? It's just the IR loops.
I thought you were saying something like in the full theory there should not be other heavy particles.
Yeah. Yeah, so the next example we'll do, the matching will be a little less trivial, okay? But actually even here, maybe I should have written them, but in these dot dot dots, I've actually expanded little m over big M, right? Just because I didn't want the nasty formula with the full log in it. And so there's actually extra corrections here that are small. So even if I picked, right, I just didn't write them explicitly, yeah.
So is this log actually small though? Log mu squared, mu m squared?
Yeah, because I get to pick, now I have an extra scale. So I've introduced a matching scale, right? And I get to pick it to make this log small.
But then you can't you can't make mu m comparable to little m.
I don't want to. So then I use the RGEs. This is my boundary condition for the RGEs and the EFT. Okay, maybe let me write the next formula. So now all right. So let me write I'm skipping a couple of steps because this is exactly what I did yesterday with the expanded out thing. So let me write this. That's an eta of mu h plus 3I over 32 pi squared, eta squared log mu h squared over mu m squared plus c4 squared log mu m squared over little m squared plus 2/3 plus 3I 2 pi squared kappa squared log mu h squared over big M squared. Okay. So this exposes the large log problem, but I hope, we'll talk about it until you get it, but if you can remember what we did last time in the RG improved example, right, you can understand where each of these pieces come and which parts RG improvement is fixing for you, okay? So let's go through it. We have our tree level coupling at the high scale, okay? So this is, where we matched string theory onto some field theory. We integrate down to our heavy particle scale M, okay, using RGEs. So that is captured by this. So this log is going from mu high to mu match. This is the RGEs in the full theory. So I would sum this log by doing RGEs in the full theory, right? Just like we did yesterday. Then, at the matching scale, in principle, if I hit the matching scale, I set eta equals C4, and I just go down to the low scale, I generate a new large log. This is the one you're asking about, okay? However, this is a log that I can sum using RGEs in the EFT now, okay? So just like this is not a large log, doesn't give me a large log problem, even if mu high is many, many orders of magnitude bigger than the matching scale, similarly here, I don't have a large log problem, I use the RGEs to sum it. And then I have this extra term that came from matching. This thing doesn't get summed, okay? This is like a finite correction. It's of order, and it depends on the scale mu high, which does not, which is not a scale that we RG, that sort of gets absorbed using RGEs, but we don't have to, because we get to pick it of order big M, okay? So again, using that picture with two large scale separations, we sum this log with RGEs in the full theory. We sum this log with RGEs in the effective theory. Those are both convergent. And we pick mu high, mu, yeah, that's right. Give me a second. Yeah, this should be match. I think it's a typo in my notes. And we pick the matching scale of order big M, right? And that keeps this log small. So we use RGEs to sum these two sets of logs, right? And then we have a matching scale which lets us set the last log to be small. Okay. So that's how it works. Okay?
So the other one needs to be perturbative, right? I mean, if it's non-perturbative, the RGE are not going to sum it because the kappa is no longer in the. I mean, well, it is. It's not. Yeah, it's not in the.
Correct. That's right. Exactly.
What does the resum magnitude actually look like?
Oh, I mean, it's just two versions of what I wrote yesterday, so I didn't bother.
Like the thing with the denominator?
Exactly, yeah. Yeah, because this is just, well, this one is just the phi to the fourth theory from yesterday. This one actually, you have to solve the coupled set of RGs I wrote, and it's a bit of a mess. So it's easy. It's very easy to check that you get the right thing expanded, but yeah, it's a couple differential equations, so it's just annoying. So I didn't write that intermediate step.
And this will be valid at one loop.
Yes, this is all one loop, exactly. But it's, sorry, let's be clear, it's leading log summed, one loop corrected. Okay? So here's the double expansion happening. So I expanded here, but of course, if I actually were doing the calculation, I would want to use the summed amplitude, right, using the RGE improvement. So here, in these two terms, when I use RGEs, I'm leading log improving these couplings, okay? So that's my alpha log expansion. I'm going to leading order in the alpha log expansion. And then I'm including the one loop corrections from the low scale, okay? That's where this little m came from. I skipped that step because we did it yesterday. And from matching, okay? So that's all next to leading order. So I've done leading log plus next to leading order, okay? In this double expansion.
Where would I remember you also said there's next to leading log somewhere, but I don't see it here. Where would that appear? Only in two loops? When we look at, I mean, when would we need to take care of that?
Good. So so it just is it depends on how large your logs get versus your couplings, right? So when you need to use leading log summation, it's when the log is of order alpha, right? When you need to go to next to leading log summation, it's when log squared is of order alpha, right, and so on. So it's a systematic. So by RG improving these, right, you're systematically summing all of the leading logs. And if you went to two loops in your beta functions or in your anomalous dimensions, that would be summing next to leading logs. And you would do that if the logs were big compared to the parameters, right? So in QCD, for example, where alpha is pretty big, this is why people torture themselves going to next to leading log, right? Because alpha is pretty big in QCD. And so numerically, it's actually important, right? In the Wino calculations, where we used SCET to sum Wino annihilation, so we have some series of papers on this, we were working with SU2, right? So the Wino, I'm making assumptions here of what you know, but right, the Wino is just an SU2 triplet, and the coupling there is the weak coupling. And working with these people who normally work in QCD was super fun because when we got the answer and we sort of checked the uncertainty is perturbative because, you know, alpha weak is relatively small, and they were like overjoyed. I mean, they had really never done an electroweak calculation like this before because it wasn't relevant to their research, and they'd never seen such a nice convergence, right? So we really like a part of why this technology is so important is if you're working in QCD or you're working in some situation with a stronger coupling, right? Because then you need to go systematically to higher and higher orders, okay, to get a convergent answer. Okay, good. So in my last half hour here, I want to talk about the hierarchy problem, and maybe I'll pause for just another moment, make sure we're all clear. Because if you understand this, then I'm going to hopefully quickly convince you that the hierarchy problem, I'm going to just show you how the hierarchy problem works in this language, okay, which avoids this there's no hierarchy problem in DIMREG crap, and then that'll be a nice stopping point, and when we come back this afternoon, we'll do this heavy light integral.
Where is the piece that would look like a data function? In the older version?
Oh, it's the fact that, if you like, it's that, let's see. It's really the difference between these, right? So I run this with the RGs and the full theory, and then I use a theta function, I run this in the RGs and the effective theory. And that's what we're doing here, by the way. It's just we've systematically included the softening of the theta function at the matching scale, right? Absolutely, yeah. So, yeah.
Is it not a physical that decides the coupling should not be like a physical quantity that you measure? So it's just like there's no way to describe it.
Couplings are not physical in QFT, right? Because they run. They depend on scale. So what?
I can measure them at a given scale. So
No, you extract the. So you have to be careful, right? What we actually do is we measure observables. We design observables that are most sensitive to those logarithmic corrections, and then we extract a running coupling and we interpret the observable as a running coupling. But it's always stated in a scheme, right? So when you look at, say, if you open Martin's primer and you look at like unification in the MSSM versus the standard model, that's done in the MS bar scheme or the DR bar scheme, right? That's a scheme-dependent statement. And if you like, where those couplings meet, what would be the capital M here, maybe, in a calculation like that? That's a scheme-dependent thing as well. That's really where those coupling meet is mu m. And what we expect is that there's some heavy particles around that scale. And when we say those kind of words, we're really talking about this kind of behavior, right? So the fact that the couplings meet at a scale doesn't mean anything itself. It's just suggestive that that there should be new particles around that scale that are going to, and then it's going to show up in this sense. Okay.
So for this expansion, you are expanding at what scale?
So what I did is I just did a more complicated version of what I did yesterday.
Yes.
Okay. So I just evaluated the RGEs to leading log, like only including the first logarithm in the calculation of the RGEs, right? The RGEs sum a tower of logs, and I've truncated that to just be the first log. And then I put all those pieces together here.
Sure, but if you are expanding, for example, at the mu L, then there should be terms related to the mu L.
Yeah, so some stuff canceled, so I skipped some steps, but this M is coming from that,
Ah, okay, sorry.
right? So maybe I wasn't totally clear, but okay, sorry. Because we did this yesterday, it's exactly the same thing. I took this boundary condition, I ran in the EFT with this RGE, and then at mu L, I calculated the one loop diagrams, right? So that's how you get the sort of finite one loop parts, right? You do that at the low scale and within the EFT, okay? Which is the scale of order of the process you're interested in, right? So that's around the mass of the particle because we're at threshold. These are excellent questions. Thanks, guys. Okay, cool. So let's do the exercise for the mass now, okay? The reason I didn't do this first is because the mass is, if you like, you should think of the mass as more of an input, right? This is something you measure in the IR. You measure the pole in your propagator, whatever, through some scattering process. And so as I belabored already, when you do matching, you need the IRs to be equal. And so you just by hand set the masses of the particles equal to each other, okay? But you can still ask this question. If I were handed masses in the fundamental theory, right? I do my string theory at the high scale. I get some field theory description. It's got some masses of particles. Some of them are light. I take that theory. I run it to the low scale using these EFT techniques, right? To make sure I've got control of all my logarithms, right? I'm controlling perturbation theory. And you can ask, what happens as you cross thresholds, okay? So what's going to happen as we go from this fundamental scale through the mass of a heavy particle, okay? So I'm going to do the calculation 2 times. First, I want to show you what happens if this isn't here, okay? So you're just handed a fundamental theory, and that fundamental theory is renormalizable. It's just phi to the 4th theory with only a light particle in it, okay? And this is where this statement that Dimreg doesn't have quadratic divergences, so there's no hierarchy problem, comes from, okay? So I want to show you why people say that, okay? And then I want to show you, once you include a physical mass in your spectrum, you say there's some extra heavy scale, why they're wrong, okay? So we're going to use the same picture. We're going to use the same model. So step 1 is no quadratic divergences in Dimreg. Okay. Now I'll just write the Lagrangians again just to be really complete, and I'll keep the mass parameters now. So let's do this first. I'm going to leave some space for them. So I want to do this without the heavy particle first, yeah?
Why do we say no quadratic divergence in quadratic divergence in direct? I mean, if we calculate from the 5 to the 4 the one correction to the mass, this is an A0 in Bergman.
Can you maybe wait? Let me do it, and then ask me, yeah, what I mean. Yeah. Okay. So this is a situation. This is my toy model of the standard model and nothing else. Okay? You with me? Okay. So matching at one loop. I have my A match, my mismatch between the two theories is equal to A full minus A counter terms minus A EFT minus A counter terms. And again, I don't have to be careful about wave function renormalization because I'm in a scalar theory. And I do this at a high scale mu m. And my full theory, so my observable is going to be the 2-point function, okay? My full theory has the infamous quadratically divergent diagram. It's eta over 2. There's a factor of 2 for symmetry factors. Mu h, or if you like mu match to the 2 epsilon integral dl. 1 over L squared minus little m squared. And that equals I eta over 32 pi squared little m squared times 1 over epsilon plus log mu m squared over m squared plus 1 plus order epsilon. Okay, so I wrote this out, right? In the other case, when we were doing the phi to the 4th corrections, right, I would have just had this denominator squared. I didn't bother writing this evaluation for you, and you had to combine the denominators with Feynman parameters, blah, 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 right? But if you look at my notes, I have a whole long section really making this point very obviously, or if you look in any appendix of any of the textbooks. But the difference, the only difference actually, it's kind of amazing, between this calculation and the one where you square it is this 1. And this 1 is the hierarchy problem, okay? In the calculation where this is squared, just you do the thing and you don't get the 1, okay? So now I can do this in the full theory. I can do this in the EFT. Yeah, that's just a statement that all of this stuff is scheme dependent, right? So yeah, so let me write the final answer and we can come back to that. Yeah, let me write. Yeah, I have something. Yeah, I'll wiggle my way out of that argument. Okay, so in the EFT I get the same thing. Right, just with eta goes to C4, right? And then, should have stolen Ruben's board. Okay, so then if I use phi goes to phi to match, that gives me minus I C4 equals minus I eta 4, or eta, right, at tree level. And so my I am match, which is just coming from this mismatch between these two, is simply the difference between these two calculations, but with this tree level condition. And so I get minus I m r squared plus I eta. I'm being really pedantic here. M r squared log mu m squared over little m squared plus 1 minus eta goes to C4, which equals 0, of course, right? Because the masses had to be equal based on this requirement that the IR of the two theories is the same. Eta equals C4 is a matching condition from requiring I get the same answer for phi phi goes to phi phi. And sure enough, I get 0, okay? So this is why people say there's no quadratic divergences in dim reg, okay? What they're saying is dim reg, so this is deeply tied to this idea of scaleless integrals vanishing, which I keep saying this phrase because I want you to remember it, and I'm going to prove it for you. I was hoping before lunch, but maybe after. What's going on here is that because our regulator is mass independent, and our log gets a factor of this mu in it, there's nothing else around. Sorry. Let me start over. Because our regulator is mass independent, and because we're correcting the mass of the particle, we need something to appear as the coefficient of this thing, which carries mass dimension. And the only thing around is the mass of the particle itself. Mu only appears inside logarithms because it shows up as mu to the 2 epsilon, right? It's a tiny little thing. When you expand mu to the 2 epsilon, you get log epsilon. You get log of mu squared, right? Plus higher order stuff that depends on epsilon. So it can only appear in the log. There's nothing else around. Just by dimensional analysis, you had to get it proportional to little m squared, right? When Matthew wrote a similar expression for this, right? He wasn't being super careful. He was honest about that, right? And he said, hey, I'm just schematically saying that this should be replaced by some high scale, right? And he mumbled the correct things about how it needed to be physical and blah, blah, blah. And so what I'm trying to do here is really sharpen that in a mathematical way. But one way of thinking about the fact that there's no hierarchy problem in dim reg when there's no heavy scales, no heavy physical scales, is the statement that if you cross some artificial heavy threshold that doesn't exist, right, but you say, oh, there's some scale up there that I'm worried about, but it doesn't have particles associated with it that couple to the Higgs, then if you match across that scale, you get no contribution to the mass, okay? Just because of this.
So if the full theory, sort of, the UV theory only has like a marginal operator, then it's saying basically here we see that there really is no hierarchy problem according to this schematic.
According to this, yeah. Now there's an awesome caveat to that actually. This is a really cool paper by Vitek Skiba, Martin Schmaltz, and other people. I don't remember, but those are the names that I do, where they play games showing that if you have some fundamental description where there's even only marginal operators, but there really is something physical happening up there, that you can actually get a hierarchy problem through the change in the anomalous dimensions. This is a super cool paper, which really sharpens the idea that if there's a physical scale, you still get a hierarchy problem, even if it doesn't directly couple to the Higgs. But this calculation doesn't show that. That requires them being more clever. Okay. Great. Okay. So now, right, I do this. My matching is 0, and then at the low scale, I just calculate. So now at mu low, just like before, I just calculate my one loop correction, and I get something. I won't write all the terms. I get something that goes like m squared 1 plus log of mu low squared over m squared. I can choose mu low to be of order m squared. This thing just is of order itself, and there's no problem, right? I get a loop factor here, and so it's just perturbative. There's no issues, okay? So that's the standard model by itself in isolation, no hierarchy problem, okay? People often, yeah, I'll complain about this now. So when people do this, I've done it before myself, more than once. people go, oh, in the standard model, the Higgs couples to the top, and so you get something that goes like y top squared over 16 pi squared, with the 3 maybe for color, and then you get a lambda squared, blah, 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 right? And this argument is really spurious. I think since we're in this age of people questioning naturalness, which is insanity, but they're doing it anyway, it's because we, the theory community, for the longest time have been super sloppy about the way that we talk about this, right? Because we just expected the new physics at the TeV scale, so we didn't have to be so careful. This is a spurious argument. But if you go to the MSSM, which is the analog of what I'm about to do, it makes this lambda physical. It becomes the mass of the stop, right, in this calculation, and all of a sudden the argument has teeth, okay? So let me show you what changes. Let's add a heavy particle.
Isn't that what you get with a hard cutoff?
Yeah, but that's a regulator independent. I mean, it doesn't mean anything, right? So the reason that people are confused about this, that people say these wrong things, is because this is naively, and you say the hard cutoff is of order the mass of some particles, maybe, but we don't really know what it is. When you put in Planck here, that's really bad, right? Because you could say, oh, there's some particles maybe at the string scale, but you really should be dressing this with something more physical, okay? And so, so let me dress my toy model up. We'll do this calculation very quickly again, and then I'll say a few more words about the interpretation, just because I think, especially for you all, since a lot of you aren't working on naturalness-related things, so you haven't probably thought about this too much, this is a really sharp point that I think every good theorist needs to understand, okay? All right, so let's go back. Let's add a heavy state, our friend big phi, and let's add our kappa, little phi squared, big phi squared, right? And then our EFT is the same, okay? And now this calculation is almost the same, except that we have an extra diagram in the full theory. So we have this plus this, right? And slow me down if I'm maybe not going to even write everything, okay? I hope it's like totally clear. You get another factor now with little m goes to big M, right? Now you get one of these with eta, you get another one with kappa, but proportional to big M squared, and critically with the 1, right? Okay? So you get, in the matching, so just like before, the contributions from these two loops in the matching are going to cancel, right? But you're left with this heavy particle loop that doesn't cancel, and you get this tree level piece plus, let me get the sign. Yeah, I got the signs right. I m r squared plus I kappa over 32 pi squared, big M squared, log mu match squared over big M squared plus 1. Okay? So, and I didn't write there's the one loop little phi here and one loop little phi, right? So these cancel, and you're left with this, okay? So now, if we take mu match squared of order big M squared, right, which is the natural thing to do, if we're doing calculations in the full theory, we want all our logs to stay small. That's what we're going to need to do, right? So we're going to pick that scheme. And in that scheme, we have M match squared is minus kappa over 32 pi squared times big M squared. And that's the quadratic divergence, okay? So continuum EFT, right, dimreg dressed up with this language of matching gives you a hierarchy problem, right? So that question about the matching scale, which is an excellent one. So if I hadn't done this, right, if instead I had picked whatever it needs to be, e to the, yeah, right, e to the, with the right m's, whatever it is, to cancel the 1, right, you would get that this were 0, okay? And so yeah, in this toy model, you could do that. But in a real theory, if you're really completing the standard model, which is what we care about, you've got lots of particles. They're not degenerate. And so you could do that for one particle, but you're not going to be able to cancel all the thresholds, right? You could argue with me, oh, but what I really want to do is I really want to do a calculation where I write down a different EFT as I cross every stupid threshold, right? And then you could introduce matching scales at every threshold, but you'd get these logs. I mean, like, so yeah. So it's definitely all of this way of thinking about it, which is, I think, really nice to think about all the different ways you could calculate this, sharpens the fact that tuning isn't physical, okay? So, yeah, so I'll be able to end on time here. So I want to say a few words about this interpretation, okay? Matthew said, I lost the top. Matthew said a lot of this stuff, and in fact, so if you're interested in this question, when I wrote these notes up, I hit this point, and then I digressed for like 10 pages about the hierarchy problem. In part because Matthew's a good friend of mine. He's perhaps the world's like leading thinker about naturalness at this point, and so I wrote up some discussion of these issues and the subtleties and the scheme dependence and blah blah blah. I sent it to him. He hated it. We went back and forth like a dozen times or something, and I ended up with something that I'm really proud of that Matthew gives his seal of approval to. I put some real effort into trying to discuss this because I think it's not carefully talked about in a review in the EFT language at least. There's lots of great people who have written about this issue even in the modern era, but nothing that really puts it in this context. Okay, and so there's a few things that I want to highlight, and then I want to encourage you to go read that, find it frustrating, send me an email or whatever. Okay, so here's the deal. Okay, even in this model, I'm cheating because I haven't introduced a symmetry that makes the mass of my little scalar phi physical. Okay. The problem is, again, all about quadratic divergences, okay? So if I set the mass of little m to 0, it would get generated by loops because it's not technically natural, right? As I set it to 0, I don't enhance a symmetry. So what you need to do to sharpen this question is you need to embed the standard model in a theory that makes the Higgs mass calculable. And what we mean technically is you need to embed the standard model into a UV theory where there's a symmetry that protects the Higgs mass, okay? So we know of two nice, beautiful ways of doing this, right? Those are the ones that have been studied to death. That's supersymmetry and composite Higgs, okay? Matthew talked a lot about composite Higgs, but the point perhaps that he did kind of quickly, he I think said this quite well when he's talking about pions, where it's also true, but in composite Higgs, what's the symmetry that's protecting the Higgs mass? It's a shift symmetry, right? So in composite Higgs, you get a Goldstone boson. Goldstone bosons are protected by a shift symmetry, okay? So then they become calculable, right? In supersymmetry, does anybody know what the symmetry is that protects the Higgs mass? Exactly, it's chiral symmetry, okay? So what happens in supersymmetry is that in supersymmetry, you relate the scalar to the fermions, right? The fermions have a chiral symmetry, and so if you had a purely supersymmetric model, the scalars would have the same mass as the fermions, and the chiral symmetry of the fermions would protect the scalar mass, okay? So when we say supersymmetry makes the Higgs mass calculable, what we're really relying on is the same idea that makes the electron mass calculable, right? It's that there's a fundamental chiral symmetry for the scalar now, right? If you like, supersymmetry gives a chirality to scalars. That's why we embed them in chiral superfields, okay? In both these cases now, we have a notion of a technically natural Higgs mass, okay? And then we can start to ask these questions about fine-tuning and naturalness, okay? But they're still not physical, okay? I personally believe that there's no observable that is sensitive to tuning, okay? Tuning's not an observable. And it starts to get fishy when you start talking about quantum field theory without observables, okay? However, here's where the sort of philosophy comes in, which is to say that if we really think about this situation where we have some fundamental scale, we have some symmetry breaking scale, and we have the standard model, right, the Higgs Vev, what we're really saying is that call it string theory or whatever, I don't care what the fundamental physics is at some level, as long as it predicts the parameters of the theory for me, right? So this is really similar to what we're doing in all of these EFT examples, right? We're imagining that there's some theory handed to us from on high, right? We have that fundamental physics theory. It has parameters in it. And then we start passing through thresholds, okay? It's presumably very complicated. There's presumably a lot of crap going on up at that heavy scale, right? So you got to integrate out a lot of stuff to get to the standard model. And every time you cross a threshold, you're going to encounter this problem, okay? So if you think that the reductionist philosophy, this approach that we've taken to fundamental physics since the beginning is going to continue, then what that means in our modern language is that the fundamental parameters are calculable in some fundamental description, okay? If that's true, then at the high scale, before you start crossing these thresholds, then the fundamental theory is going to have to give you something which is big M squared plus a tiny bit that's left over, right? Such that when you cross the threshold and you do your matching, the big M squared part cancels and you're left with little m squared left, okay? So when we say that the hierarchy problem is a real problem, right? When we talk about tuning, the calculations of tuning are, I frankly don't necessarily like them, and you'll see people arguing about tuning measures and whatever, and that is a waste of time, okay? That doesn't mean anything. It's not physical, right? You're not asking a physical question. But what is interesting to ask is whether or not you can come up with a mechanism which either qualitatively changes the way we think about where that tuning came from, like the relaxion, for example, which is really qualitatively different than symmetry solutions to the hierarchy problem, or if you're comparing, say, tuning in one example versus tuning in another example, then it starts to be, at least if you're doing it in the same scheme, right, you can start to at least squint and maybe feel like you're learning something, especially if you get a big improvement, okay? So I encourage you to be critical and skeptical of anyone who starts talking to you about tuning as an absolute thing, right? If someone says the tuning currently in the MSSM given the LHC limits equals, 1.3% or something ridiculous like that, that's you should be skeptical and you should push back, okay? If someone tells you that I wrote down a new model and in my model the tuning with respect to the MSSM is tilde improved by a factor of 2, then you could choose to find that interesting, right? That's qualitatively changing something, okay? You may not care about factors of 2, and that's your prerogative, but there are certainly people who do, okay? I would probably say a factor of 10 is maybe more interesting. So anyway, the point I really want to stress here, right, is because my charge is EFT, but we're here doing BSM. So the presence of this log and the great question that you had about choosing the mu, right, is exactly nailing this point, okay? It's that the matching coefficient is scheme dependent, it's mu dependent, right? It's not physical, okay? But if you can embed this whole story into a framework where the fundamental parameters are calculable, something very strange is definitely going on to get us down to the standard model with a light scale, okay? In other words, this is just telling you, right, without symmetries protecting the masses, that when you cross physical thresholds, those physical thresholds are sensitive to those mass scales. It's inevitable, right? And so that's the way we dress this idea of quadratic divergences. That's the way we say, so that's the sense in which calculating quadratic divergences or studying the impact of quadratic divergences using cutoffs or using dim-reg, right? You can make all these things agree if you're careful, okay? And so this is the way to do it in dim-reg, right? You need to. So the thing that I really hope you took away from this first lecture is really this idea of how to marry the intuition that heavy physics should decouple with this mass-independent regulator scheme, which is dim-reg, okay? Dim-reg is super easy and convenient to use, and so we like it, right? It also doesn't break the symmetries, so we like it, but it doesn't manifest decoupling, and so we need to dress it by EFT, okay? And in particular, we have to do matching calculations in order to capture the physics of decoupling, okay? And in doing that, we get our change in the beta functions or change in anomalous dimensions as you cross thresholds, and we can do that in a controlled way. And we also, and so that you should like because we see that in nature, right? When you extract running couplings, you can see those kind of threshold effects. And so if you buy that approach, then you're forced to buy this too, okay? All right, so I'll stop there and take questions, and then this afternoon what we'll do is I'll show you something really genuinely that I think you probably haven't seen before, which is how to use these techniques to deal with logs that only have physical scales in them, okay, and how to resum those kind of logs. All right, thanks. Yeah, take questions.
Sorry, I'm still a bit confused that here the physical scale is the capital M, which is the some physical particle spectrum mass, and then for the mu, it's physical. So we can choose whatever threshold we want to do the matching.
Correct.
And the result is that there's no large correction because we can choose the log mu over m to cancel the 1.
Yeah, but again, this is.
Why is that the problem? Because the mu can be arbitrarily chosen.
But this is in a theory. So if you want to say that there's one heavy threshold in nature and that all the new physics is exactly degenerate at m, and that I'm only in one very particular scheme, am I allowed to ask this question? Then I mean.
No, I can do this every time I cross the threshold.
No, look. Think about weak scale supersymmetry. So you've got a particle spectrum. You've got two stops even in supersymmetry. Their masses are not going to be equal. They're even broken by electroweak corrections. And so, but they're nearby. And so you don't have any large logs. You only need one matching scale. So you can't even do this in the MSSM, right? So it's really is missing the point. The point is that the presence of this makes the question scheme dependent, which is a sign that it's not directly physical. Okay, that's the takeaway. If you want to play games with picking a particular scheme where there's no matching, you're welcome to do that. No one will pay attention to you. I mean, it's just not that's really missing the point here. Okay, because again, I did this very simple toy model, but I encourage you to go play these games in the MSSM in a more realistic theory, and you'll see that really this is not buying you much of anything.
Sorry, I guess I just don't see what is the reason. Okay, sorry, I should rephrase. I don't see the reason that prevents me, the factor that prevents me from doing every time I match something to a EFT, and then next time I match this EFT to a different EFT at a lower scale. Even if I have multiple scales, I can, in principle, do that one at a time.
So yeah, but the what you need to do, you're going to match and then you're going to run, and you're going to match and you're going to run, and the running generates these corrections as well. So
Sorry, this is already at the mu low, right? This is already at mu low, so if I choose the mu high.
No. This is at mu. This is at the matching scale, right? So you're doing the tuning at the matching scale, right? If you like, you're picking the matching scale very, very, very carefully to eliminate the tuning. But I guess I don't understand. I encourage you to sit down. So sit down with a pencil and try to do it. In this simple case, I think the takeaway here is that it's scheme dependent, right? So you need to choose some scale, but yeah, you're not gonna solve the hierarchy problem by picking a scheme. It's just not.
I guess that's the part that I don't see from this example, or am I missing?
Well, no. So this example doesn't make that point. You have to generalize this example. So that's why I'm saying you should go do a multi-scale problem, and I hope you'll find it convincing, but yeah, I don't know what to do other than we don't have time to do it here, but yeah.
So it's something I already started understanding in previous lectures, but I haven't had the chance to ask it. So even if we have supersymmetry or whatever, you still need that at the fundamental theory, at the high scale, the bare term is going to be very, very small. Now it's not going to be a very large number plus a small number, right? But the technical naturalness means that I can start with a very small number and I stay with it. How is that not weird? I mean, it's still, unless you solve it via some anthropic or landscape, whatever, and then you don't need to solve it that way, right? Because if you have anthropic or landscape, then you just tune however well you want. I mean, you're still saying the mass of the Higgs needs to be 10 to the minus, 19 no, 10 to the minus 17, whatever, right, times n prime. And I mean, why? I mean, isn't that still a weird thing that our universe would work with? Like, I mean, Theia QCD is 10 to the minus 10, and we are thinking, why is it so small? I mean, you can tune 10 to the minus 17. That's, I mean.
Good. So yeah. So just for example, in supersymmetry, right? Okay. First, let me start with. You should ask the same question about QCD, right? So the QCD scale is of order GeV. You should say, where did that scale come from, right? So we all know there's this beautiful story of dimensional transmutation. So if you like, just as a classic example, you take supersymmetry and you need to add some dynamical supersymmetry breaking to it, and there's a huge literature of essentially relying on dimensional transmutation to break supersymmetry, okay? So similarly, there are techniques, once you have the technically natural mass parameter, there are nice ways of generating hierarchies of scales in a technically natural way, okay? So you can dynamically realize the small mass parameters in the fundamental theory, and then what's different about the calculations like this is as you cross the heavy thresholds, they just don't contribute to the mass, right? Because the loop of the tops cancels against the loop of the stops, or however you want to think about it, right? But really, like at a more a better way of saying it is that you're as you cross the thresholds, there's still a symmetry protecting you, and so you don't generate these quadratic corrections, right? So there's so people have spent a lot of time thinking it's an excellent. I mean, you're right that there's definitely some separation of scales. There's a big hierarchy, but there's a difference. So solving the hierarchy problem is making that hierarchy stable, right? And then there's a whole literature of model building that hierarchy, which is super interesting, but I would say a different question. Okay, maybe another thing I can say that might help you is this is not the only place the matching scale appears, right? So you need to pick the matching scale conveniently in order to, you're going to want to build these EFTs in order to actually do some calculations too, right? So, I think that if you, so I can admit I haven't done the exercise of like putting some set of things very close by and actually trying to integrate them each out over and over and over and generate this tower of EFTs, partly because it would be painful. But the thing is that you're really going to need to choose. So when you actually have the multi-scale theory, this is a part of the issue, is the multi-scale theory has loops that involve all those masses in it, right? And so what you're going to want to do is you're going to want to be picking, so you can have a log with a matching scale and then a function of all the masses in the theory that's going to appear in, say, the 2-to-2 scattering calculation. You're going to have a different log appearing in the mass correction calculation, okay? And you're going to want to simultaneously make both of those logs small. So you're going to pick this choice here, right? But at the expense of affecting the logs that happen in other calculations. So if you really want to self-consistently tell this whole story, it's not this doesn't exist in isolation, right? The EFT has to do something for you. It has to calculate physical processes in a controlled way. And so there's another thing which I'll say, which is totally hand wavy because I haven't done the 2-loop calculation. But the other thing is that this will break at 2 loops. So even if you believe that you can, scheme choice away the 1-loop hierarchy problem, you're not going to be able to do the same thing at 2 loops, right? And so again, this all highlights that the tuning is scheme dependent, but that's why absolute tuning is not meaningful, right? So if I build you a theory with where that's just the MSSM and you play your game, and then I build you a theory that's an extended version of the MSSM where I claim the tuning is better, I'm going to want to pick the same scales. I'm going to want to do everything about my EFT and renormalization the same to be able to compare apples to apples, right? And so again, you may be able to like turn it off in one, but not in the other. So I think it really misses the point. So again, the fact that it's scheme dependent is very important, right? Because that's the highlighting that it's not physical, but sort of trying to wish the problem away by picking a scheme is I think missing the point.
Because I think this is because I think this is a good place for us to break now for lunch, and then you guys can continue asking questions for Tim.
Yeah, I'm
Lunch
happy.
or later. Okay,
All right.